the energy system that we have studied up to now and processes is mainly the fact that we are going to combine process technologies together and process units in order to make processes that are integrated. So the goal is to first introduce what is a process system design, present the methodology that we have developed in order to make this process design, discuss how we can use process integration techniques in order to make the process design. In the afternoon, we will discuss about how to integrate sustainability measures in the process design. And I'm going to discuss about the use of optimization techniques in order to make the process design and to do system analysis later. Okay, so what is the definition of process design? I could have used the slide that I have used in the beginning. So the goal is to convert to supply services from resources by assembling technologies that do the conversion, and we would like to have something which is efficient in the sense that it will convert maximum of the resources into the resulting products or services. Okay, so we have to look at what is inside the design, and if you look at what is inside the design, then we have to define what are the types and the size of the equipment, the way they are interconnected, and the way they are operated. So easy to say and not necessarily easy to do, right? One of the reasons is that of the difficulty of this system is that today there are a lot of people that are developing new technologies. And I think that if we look at the history, so I'm there since 20 years as an engineer, what I can observe is that the number of technological options that are available for designing energy systems is much bigger than in the past. There are a lot of people that develop new catalysts, new types of reactors, new type of technologies to convert the energy. And something which is also very important is that we know that we have to work with multiple services. So not only one, but several services, which means that also we have to understand and to try to valorize the synergies. In addition to this, we are working in an uncertain environment. So we have the services that are most of the time stochastic, the energy prices and the investment, which are really most of the time uncertain. We have an environmental pressure that is increasing, and we have the performances of the technologies that are not necessarily always reachable. At the end, in addition to this, we have to try to maximize the use of the renewable energy resources, which includes, in fact, adds also another dimension of the uncertainty. And in addition to this, when you are looking at processes, industrial processes, the energy is at the same time the resource that is used in order to make the product and the driver that is converting the product. And this is also something which is important. If I'm looking, for example, in the biomass production, the biomass is on one hand used as the carbon support to make the product, and the biomass is used as a heat source, for example, for doing the conversion. So it means that we need to have a comprehensive approach for the process design. And what I could perhaps also add to this is that there is a difference between doing an energy system design or process design and doing the analysis. So there are a lot of people that do energy system analysis by just collecting data in literature. Okay? And the goal is most of the time, the people that do this energy system analysis try to model the market. It means that they need cost. They take cost in the literature and they say, okay, this is the cost. So, but it means that the new technologies or emerging technologies never emerge unless you have modeled an emerging scenario for the technology. And typically, if sometimes they satisfy, but it's even not clear that they are satisfied, that those approaches are based on the energy and mass balances, but at least the model are not, the processes are not modeled. And there is no engineering decision in it. So it's just mimicking or try to model the economics in the energy system to supply the services, but without looking at the real decisions that we have to take. The process system design is not an LCA analysis. So, sometimes people say, okay, if I'm doing an LCA, I'm also doing, let's say, energy systems modeling, but the reality is that the LCA is again based on the literature data that are published somewhere, which means that they are representing the mean decision or the well-chosen decisions of someone who has already taken the decision. So it means that there is nothing there that is pushing towards the efficiency. Okay. In addition, the LCA is often based on scenario, which are defined a priori. So you define different options to be compared, and you do not have any rationale to decide what are the best options. And this is also something which is that it has to be understood. The LCA typically is not doing, again, process engineering decision, and most of the time the decisions are not geolocalized. So it means that they are mainly considering mean values. So for example, you consider the mean energy consumption for producing 1 unit of a product. Okay, but you are not considering that this product is produced in this place and that the heat that is resulting from the conversion can be used in order to heat the city which is nearby. Okay, so LCA does not allow to do this, or has to be adapted at least to take this into account. So what is process system engineering? So the goal is to be able to do to model the impact of engineering decisions. So we take decisions and then we would like to see the effect. So I'm deciding to buy a new heat exchanger or a new reactor. We are going to use optimization techniques in order to represent the decisions that we have to take at the level of the system. Okay. We are going also to synthesize the knowledge that is generated by the people that are doing experiments, that are developing new technologies. So it means that we have to translate the experiments into models that allows us to model systems. And at the level of the system is the characteristic of the process system engineering approach. It means also that we are able to adapt the design to the specific conditions in where the system will be developed. We have to look at the whole system. It means that we have to understand the system integration, and we can use the environmental impact as a way to measure the efficiency of the decisions we are taking. Okay, so it's a way to it's an indicator that we can use for helping in taking decisions. Okay, this I have already shown, so we have discussed a lot already those in the previous days. And what I can tell you is that when we solve a process system design, we are learning a lot. And I think that if I have to look at the major outcome of the application of the process system engineering techniques is the knowledge that we are generating. And I can tell you that I'm always surprised by the speed at which young engineers do learn new processes by applying this kind of techniques. The example is that in 6 months, you have students that are able to ask questions to people that are really experienced, saying, okay, why are you doing this, this, and this? Okay? And have the people blocked on the answer because they do not know. Okay? So this is, I think, something which is really important. Understanding the system is very important. The techniques will be used in for different applications. I'm just making a list of what we are working. So CO2 capture in power production, producing hydrogen, producing biofuels and biorefineries, integrating fuel cells. But it can also be, it has been used in water treatment and also water production. And of course, we have seen the urban systems. There are several applications there. So, what are the questions? And for given the questions to which we are going to answer for the process system design, I'm going to use a simple example. So, a simple example is using wood. So, wood is a carbon hydrate. So, it's one molecule, one atom of carbon, 1.3 of hydrogen and 0.6 of oxygen. So this is H2O. So it's water. This is associated with carbon. And this is a typical composition of wood. So if we take this, if we add a certain amount of water, then we will be able to produce a certain amount of methane and a certain amount of carbon dioxide. So this is just a stoichiometric calculation. And this is exothermic, so it means that we will release heat. So this is the simple problem definition. And when I have to solve the process system design, I have to look at what are my options first. And among the options, then I can have a list of possibilities. So if my biomass is solid, then I can do combustion and I can produce heat or electricity. But of course, I will go towards a more efficient way, because I can, so I have different options. I made the list, and of course I'm going to go to this one, where I can convert the solid biomass by gasification in order to produce producer gas, and can then produce the transportation fuel that I need. Okay. Once I have identified the options, then I'm going to define what are the necessary steps. So, for example, if I have to produce fuel from biomass, I know that I have to decompose the biomass, and then I have to do the fuel synthesis. I have different options for this. Here, I can do gasification or pyrolysis, and I can then obtain different types of fuel. I would like to look at the methane, but I could use other options, and I have to be aware that there are other options, because perhaps that the other options are better than the production of methane. Okay, so once I have identified the major process unit of the major operations that have to be done, then I'm going to look at the processing options. And what you can see is that as soon as I'm starting to look at the way, for example, to decompose the biomass, what you can see is that you will have a lot of options. So, for example, if you have wood as a resource, then you can have different types, different ways of drying the biomass, different ways of converting it. So you can do torrefaction, you can do pyrolysis, then afterwards you can do gasification. The gasification can be done in different ways as well. You can have different types of gasifiers. And then you will produce syngas. The syngas can be then, again, treated in different ways. And I can continue like this, because after the syngas is produced, then I perhaps have to adapt the stoichiometry, perhaps extract the carbon dioxide, then do the methanation in order to convert the syngas into methane. I will have here a combination of carbon dioxide and methane, and with different options, I have different options to separate the methane from the carbon dioxide to end up with my end product, which is the synthetic natural gas, and the byproduct, that is the carbon dioxide. Okay. So now, if I want to be able to represent and to make decisions, so I have to choose the technologies here. So I have a list of technologies with a lot of options. I'm just making the inventory. So it means that now I have to model each of the process units. And so I'm going to look at developing models that allows me to analyze what is the efficiency of the conversion. And the models have to be, on the one hand, detailed enough to represent the reality of what is happening inside the process unit. So just using a conversion is not always the best way of making the conversion. But they do not have to be too complex. Okay? Because if you have to go into the CFD in order to model a gasifier while you are not sure that you are going to use this gasifier, well, perhaps it does not make sense. So you have to make a compromise. So I'm using the citation of Einstein, so the models have to be simple but not simplistic. Okay, so this is where we have a compromise. One thing that we have to understand is what is the relationship between the conversion of the flows and the energy that is needed to realize it on one hand, and on the other hand, the equipments that are needed. So we need to be able to size the equipments and to size the in order to be able to estimate the cost. And of course, we are going to use the available knowledge, and the available knowledge is mainly coming from literature, plus the experiments that we could do if we have access to experimental facilities. So which means that we have first to look at the degree, when we have to develop the model, so we declare the level of detail that you want to reach, and then from there you will define the degrees of freedom that you have, and the degrees of freedom will be based on the one hand what we want to model. So you have learned degrees of freedom as being related to the number of compounds, and of course if you want to go into the details of the gasification with all the composition of tars and tars. Missing one word. So the heavy compounds which will be in the gas phase. You have to declare what you need, okay? And once you have this, then you know the degrees of freedom and you know the level of detail in which you have to go into the modeling of the system. Then you have to ask yourself what is the best way of doing the modeling, especially considering that you do not know the design of the system because this is the result. Okay, so the gasifier is not known, you have to design it. Okay, which means that sometimes you will use some tricks, like for example here the gasifier is modeled by the equilibrium reactions. But the equilibrium that you say, okay, I'm not sure that I'm going to reach the equilibrium. So that what you can do then is to try to use some experiments in order to calibrate the values, the parameters of your model, so that they represent what has been observed. But the advantage of having these types of models is that you represent the thermodynamic operations. So if I'm writing down the equilibrium, the chemical equilibrium, it will be there will be a link with the temperature and the energy balance. It means that if I'm deciding to operate the gasifier at another temperature than the temperature that was observed, I will have the trends which will be represented, and I will see what is the impact on the composition of the syngas that is produced. Okay? So, and this is a question of compromise. So we have to really go into the analysis to understand what is happening in each of the process units. So the goal of the models are to be able to represent the conversion and to represent the interfaces that each process unit operations are going to present to all the other process unit operations. So among the interfaces, you have the mass exchange, so the flows, but there are also other interactions, for example, the heat integration, the heat interactions that we are going to model with the heat integration techniques, okay? Or the power consumption or production. So if you have compressors, if you have crunchers, you will have electrical consumption, for example. And we would like to be able to see the link between the process units and the energy conversion system. And for doing this, then we are going to use the process integration model. So the process integration model can be either explicit, so we could model all the heat exchangers, but as we are at the level of the design, we will not use this technique because we do not know where are the heat exchangers. So what we are going to do is that we are going to use the heat cascade as a way to model the heat exchanger network. Okay, so now what does it mean? It means that I'm not going to model the heat exchangers. I'm going to use a trick, which is the representation of the heat cascade in order to model the heat exchanger network. Okay, what is the goal? I have to be able to identify what is the heat recovery in the system. I would like to close the energy balance. It means that I have to introduce the combined heat and power options in my system. And I would like to know what is the cost of the heat exchanger network. Okay? So for defining the heat recovery, I know that the heat cascade is a very good solution. And in addition to this, I know that, that I have shown you the technique in order to calculate the combined heat and power production and how we can close the energy balance by using the mixed integer linear programming formulation of the heat cascade. Okay? Which means that I'm introducing all the flows in the system, all the options, and I can use the optimization in order to decide which are the one, this one missing here, because the heat cascade is missing here. I know that I can solve calculate what is the flow in each of the sub units in my system by solving this mixed integer linear programming. And what I'm going to do in my calculations is to minimize an objective function, which will be the exergy losses of the system so that I will maximize the efficiency of my conversion system. Okay? So, how do I calculate the cost? There are two dimensions. The first one is that we have to realize that we know that the cost, the heat exchanger area is a function of the transfer coefficient and the logarithmic mean temperature difference. And we know that this logarithmic mean temperature difference is finally represented in the heat cascade by the delta T minimum. The delta T minimum that we can link to the hot and the cold stream, which can then be linked to each stream and to the heat transfer of the coefficient of the stream. So what I'm recommending here as a value is a contribution to the delta T minimum for each of the stream, which is equal to a parameter, which will be common to all the system, multiplied by a factor here, which will take into account the fact that we can have streams with different sizes, with different heat transfer coefficient, and that are related to a specific exponent for the cost coefficient. So this can be, we can demonstrate that the delta T minimum is following this kind of rules, which allows them to represent to use this value as being the sizing parameter for the heat exchangers that I will have in my heat exchanger network. And this is very important because it allows to have one single parameter that is going to optimize all the heat exchangers that I will have in my system. Okay, which is very important. Okay, so once I have this, then I can calculate the heat cascade by considering the corrected temperatures, and from the heat cascade, I can calculate the overall area that would be needed by all the heat exchangers that utilize the heat exchange between the hot streams in the system and the cold streams in the system. And don't forget that what I have done by solving the mixed integer linear programming problems, that I have closed the energy balance. It means that now the reality is that this part is closed there and there. And so I will be able to calculate the overall heat exchange area by saying that by summing up the contributions of all the streams and by looking at the delta T, the logarithmic mean temperature difference in each of the vertical sections that are identified in my system, in which I will take into account the heat transfer coefficient of each of the streams. Okay? So now I have a way to calculate the overall heat exchange area that is needed in the heat exchanger network of my system, including combustion, including steam cycle, including Rankine cycle, including heat pumps, etc. Okay? I have a way to calculate the amount of area that is needed, and it takes into account the heat transfer coefficients as well. If I have the overall heat exchange area, unfortunately, the cost of the heat exchangers is not linear. It means that the cost of the heat exchangers will not be the same as the cost of the area of the exchangers. So I need to have a way to estimate how many heat exchangers I will have in the system. And for this, I have a formula that is coming from the pinch theory that is telling me that the minimum number of connections is equal to the number of streams minus 1, plus the streams that cross the pinches minus 1. Okay? And as soon as I have solved the optimization problem of flows of the utility in my system, I will have the number of streams here, which means that I can calculate the minimum number of connections. And then I'm going to make a big assumption. I'm going to say that let's assume that each heat exchanger in a system will have the same area. So I'm taking the overall area, dividing by the number of units, and I have the area, the mean area of the n heat exchangers that I have calculated here. Okay? This is a big assumption which is overestimating the cost. Okay, we can prove that it is overestimating the cost. And what I'm going to do now, if I have this, I'm going to calculate the estimation of the heat exchanger network cost by summing up the cost of each of the heat exchangers in the system that will be multiplied by the number of heat exchangers. Okay, and this will give me an estimation of how much I will have to pay to realize the heat exchange in the system. Okay. So I'm going then to model each of the process unit operations, define the hot and the cold streams that are corresponding to each of these process unit operations. I'm going to combine this with the closing the energy balance. So for example, the gasification is endothermic. So I will use either the syngas or the fuel, the depleted fuel here to satisfy the heating needs. And something which is interesting here is that as I'm using the resource and I have to close the energy balance with my resource, the better I am in the heat integration here, the more I will have in this line. Okay? So I will have to write an equation that says the amount of syngas that goes in this line is related to the amount that is consumed for closing the energy balance. So it means that now the quality of the system of the integration is influenced by influencing the production. Okay? And I will include this as a constraint in my mixed integer linear programming problem. In addition to this, I will have to include the combined heat and power production. So I'm doing combustion here, and the combustion can be used in order to produce high pressure steam that can be expanded into turbines before being sent. For example, low pressure steam can be used in order to produce the steam drying requirements. Okay, so now I have to have a system which is completely integrated, and of course, if I'm exporting electricity here, it means that I will perhaps need more combustion to satisfy the needs of the electricity production there. Okay. In addition to this, I'm just showing here one example. I can have also additional ways of using the electricity, for example, by doing electrolysis, which would allow me to add hydrogen here, and to reuse the oxygen for the gasification. Okay, so it's again a really integrated approach for the whole system. And this allows me then to calculate not only the amount of heat, but also to calculate the amount of mechanical power that can be produced by the system by calculating the flows in the steam cycle, for example, and the mechanical power that can be produced. And I can then, therefore, calculate the performance of the system. I'll give you one example. So this was the reference case. And what we have done, so these are the flows. So from 100% of heat entering here, 98 is converted into syngas, but 80 go into the methanation and 18 go to the combustion, which finally goes into an efficiency of 68%. If now I'm changing the technology, I'm using another technology for the gasification, then I'm ending up with this situation, which is circulating fluidized bed system, where instead of having 18% of the energy that was needed for satisfying the gasification, this is a directly, it's a partial oxidation in the gasification, which allows then afterwards to have a higher efficiency at the end. So two different technologies convert the flows in a very different way. Okay? Yeah. So see, you see here? So
the bottom is open, the balance is open at the front.
Here, this part? Yeah. Okay. A steam cycle is a closed cycle. Okay? In which you have heat that is entering, heat that is leaving, and the rest is mechanical power. So now if I'm looking at the hot and cold streams, okay, this part minus this part is in fact the balance of the mechanical power. Okay, so it means that this the point which is here minus the point that is here is the net mechanical power that is produced by the steam cycle. Okay. You can see here that the drying is here. So in this case, it means that over the 20 megawatts that is consumed in form of wood, I would read here, yeah, that 1.5 megawatt is consumed for drying.
Does it also depend on the type of wood?
Yes, of course. It depends on the humidity, and it's even more smart than this because you have to mix wood with water. So that it means that the level of drying depends not only on the type of wood that you have, but also of the amount of water that you need. So you will go up to a certain level in the drying, which is, and there is an optimum level. Otherwise, you have to add steam in the system, so that's what makes sense. Okay? So, what I'm saying here is that now I have an understanding of how I'm converting the system. But in addition to this, I would like to know what is the cost of the system. So I'm going to now take all the flows that have been calculated by the process integration and process modeling in order to calculate the sizes of the different elements that I have in the system, so that I will be able to have a cost estimate, which will then allow me to calculate how much I will have to pay. And this leads to this situation where I will have a repartition of the cost for the different systems within the conversion processes. So the different conversion processes have different cost, and I will be able to say finally, okay, for this 20 megawatt gasifier or wood feed, this will be how much I will have to pay for the different technologies that I have here. Okay, and this gives very interesting information because now I have on the one hand what is the efficiency of the conversion, and on the other hand what is the cost of my system with a repartition. So who is costing the more in the system? Now, combining the investment with the efficiency allows me to calculate how much it will cost to produce 1 unit of synthetic natural gas based on the different technologies that I have identified and based on the cost, of course, of the wood. And you can see that it takes half of the price, more or less. On the valorization of the electricity that we could perhaps export, okay, and of the investment cost, which is related to the different elements that we have identified. So now we have the complete representation, which allows us then to make some analysis of what are the best systems. Now, if we realize that within the definition of the process we have some decisions for which we do not have any rationale, then you go to the optimization and you are going to say, to ask the optimization to calculate what is the best decision variable, for example, for the humidity at the outlet of the dryer, for the temperature and the pressure in the gasifier, for the temperature and the pressure in the methanation, for the separation in the separation. So you have a collection of decision variables that you are going to optimize, and this will allow you to, and we will do it with a multi-objective optimization. The reason for this is that we would like to have a knowledge about the decisions we have to take, so we are not interested in one single solution, but to a collection of solutions. And this is one example of the results that we obtain. So for example, here we have on the one hand the efficiency, on the other hand the specific investment. So one of the points here was described before. So one of the point was one of the design that is here, okay, in which I have all the details. So I know how much each process unit is costing. I know what are the flows and what is the efficiency. And here I have generated a list of solutions. Okay, so this is a set of solutions that corresponds to different operating conditions in the system, pressures, temperatures, etc., and the flows as well. So what is interesting here is that you have the list of options as a function of the efficiency. So the more efficient the system is, the highest is the efficiency. And what you can see is that going from 62 to 66 does not cost too much. Going from 66 to 68, you double the cost. Okay? So it's important to identify that the technologies are to some extent blocked in this case. Okay? So a few words about using the multi-objective optimization. What does it mean doing a multi-objective optimization? So I can explain it when I have two objectives. I have objective 1 and objective 2. If I'm taking one design here and I want to optimize it, I can decide that I'm going to minimize the objective 1 for a certain level of objective 2. And then we'll end up with this point, which is the best, so the smallest cost for this level of the objective 2. Okay? If now I'm changing objective 2, I can go here, and then I will optimize again, and I will end up with this point. Okay? And the reverse is also true, so I can also take this point and calculate for a given value of objective 1 what is the lowest value for objective 2. Okay? This is the principle of the multi-objective optimization. And there are different ways of solving this problem. So the first way is by using optimization, deterministic optimization techniques. And if I had to do this, so what I'm going to say is that, okay, let's take objective 2 as a parameter, and let's solve the problem of minimizing the objective 1 for calculating the decision variables for minimizing the objective 1 by adding an inequality constraint that says that objective 2 cannot be lower than the parameter. Okay, so what I'm doing here is I'm calculating so you see that if I would like to still decrease the objective 1, I would have to go there. Huh? But if I'm blocking the objective 2 to this point, then I will end up on to this value, then I will end up with this point. Okay? So it's like it's a the objective 2 becomes an inequality constraint that applies to the first problem. And then what I'm going to do is that I'm going to change the value of the parameter. So I'm going from here and I'm progressively going to here, and I will have therefore a set of optimization problems that will be solved, that will generate the curve which is here. Okay? And for your information, the Lagrange multiplier, which is the strength of these constraints on the objective 1, is giving me the slope of this curve. Okay? That means that if you have an indirect search method to solve this problem, okay, you will obtain the Lagrange multiplier of the objective 2, which will indicate the direction of the next search in the parametric optimization. In fact, in the method that we are using an evolutionary algorithm instead. Okay? And the evolutionary algorithm is going to solve the problem in another way. So it is just going to observe what are the performances. So if you receive 2 performances, then you are going to look if in the population you are going, in fact, so if you remember the way the evolutionary algorithm is working, the evolutionary algorithm is generating a population from an old population, and the old population is generated by eliminating the ones that are less good. Okay, when I'm going to define who is less good, I'm going to look if I'm dominated with respect to the 2 objective functions, or if I have 3 with respect to the 3 objective functions. If I'm better than someone for one of the objectives, I'm remaining in the population. If all the points are better than me with respect to all the criteria or all the objectives, then I will be eliminated. Okay, and then the ones that are not eliminated then serve to generate the next generation. Okay, which allows them at the end to have a curve like this, which is not always really clear. Okay, and one of the reasons it's not clear is that we would like to preserve the variety on one hand, and we would like to understand the competition. So what we do is that when we maintain the population alive, we consider that the population is organized by islands, I would say. Okay, so you have China, you have Europe, you have the possibility of crossing between China and Europe, but you say that the China will develop by itself and Europe will develop by itself, preferably. Okay, which allows to have groups like this. This is a clustering technique. Okay, so we try to group the population into subclusters, and this is important because in the system we are taking decisions. It means that it's very difficult to solve it with a deterministic approach because we have germs when we solve the process integration. Okay, sometimes as it is a mixed integer linear programming, the value of the decisions are going to create discontinuities in the system, and it's very important to see and to have this appearing in the objective function. And for your information, we can combine the 2 as well. If we want to accelerate and have a much better definition of the Pareto curve, what we can do is that we can take the points which are here, so the ones that are here that are created by the evolutionary algorithm, and at a certain time say, okay, let's then solve the optimization problem so that it goes, let's minimize objective 1 subject to the value of objective 2 that is observed, and then at the same time, let's take this point and optimize the, maximize in this case the objective 2 in such a way that it will, while having a given value for objective 1. And this they can then be done with a indirect search method, which will be very efficient because we have a starting point, and this will push, in fact, the set of solutions here into this Pareto front, which is much better or clearer. Okay, so it means that you can always combine an evolutionary algorithm that is then used in order to initialize the indirect search methods that will then push towards the best solution and to satisfy the optimality criteria. Okay, so this is a trick that we can use if we want to increase the efficiency of the calculation.
And finally, what we optimize the two functions, how we decide that each of these points should select?
I will give the answer in a few minutes if you don't mind. Okay, so the advantage of using models which are parameterized and that are doing the size after the system integration is that you can also calculate the system with different sizes. And so, for example, here we have made the calculation for different sizes, different types of processes, and looking at the specific investment. And we can see that there is obviously the trends that is well known in the chemical industry. The bigger the plant, the lower the cost. Okay, but we have also jumps. We have also jumps. For example, when I'm here, I can do it with one single gasifier, but after a certain time, I need a second gasifier. That's what is explaining the jumps. So it means that, of course, I have to go to exploit the maximum of the typical size of a gasifier to be with the lowest cost. But something which is important then is that we have also the way, because I can then plot a curve here, which will be then a cost function of a synthetic natural gas plant. So this can be used then if I want to do the design of the city that is integrating this type of plant. Okay? There were a lot of options, and because we have a lot of options, then we need to calculate a lot of Pareto curves. Okay? And this is one result for the design of the methane production processes with different type of technologies or combination of technologies. Each point is a design. Each point in the list is a design. And we can see the competition between the different technologies. Of course, if there are some uncertainties in the calculations, then we will have perhaps to negotiate in order to make this process as good as this one in terms of cost. Okay, they have the same efficiency, or given efficiency, perhaps that this one could, by a small modification or negotiation in the cost, become better than this one. Okay? For your information, calculating this curve on a single computer would have taken 1.5 years of calculation. Okay? So the advantage of using an evolutionary algorithm is that 2 points have no link one with the other. It's a population that is evaluated, which means that if you have a parallel computing facility, then you can calculate hundreds or thousands of processes at the same time. Okay, which means that at the end, the parallel computing facility did work for 2 weeks to generate this curve. It was around 100 processors. So it's a parallel computing system. Okay, but this is of course one big advantage when we have to do those calculations, because of course behind this we have the complete design of the system. So we know the size and the flows in all the elements in the system, which allows them afterwards to know what is the best solution. So I don't want to go into the details because I would like to add one dimension. And the dimension of that is related to the size is the logistics. So it means that depending on where you are, you have also to take into account the cost. And for example, here you have how many kilometers do you have to travel in order to feed the plant with a certain of a certain size, depending on the place where you are. So if you are in a dense zone where you have a lot of trees, then you have to travel less than if you are in a zone where you do not have a lot of trees and perhaps a lot of mountains. So which explains why it's important to have this the sizing parameter as well. When you this afternoon, you will learn about how the LCA can be included in the analysis. And the reason why we have to introduce the LCA is that we are going to create emissions when we transport the wood, for example. Which means that we have to decide what is the best size of the technology, taking into account the impact that we create on the environment here or even here. And we can, and what is important is that we have to take the design about the different elements in the system that is going to create the need for supporting materials or the need for buying for materials to build the equipment that will have an impact, an overall impact. So, and this is why we have attached to the economic evaluation another model, which is the model that is doing the life cycle analysis. And to show you what is going to happen now as a function of the size of the gasifier, if you want to minimize the environmental impact, most of the technology says that you have to go to a smaller size. Okay? Mainly because you have to avoid to transport wood over a too big distance. There is one exception. This one here, which is an oxygen-blown pressurized gasification, where the size is going in the reverse direction. Okay? And for your information, this is the benefit of doing the process design in an optimal way. So you have more or less 15% increase in the efficiency by doing the design. Okay, I will go fast on top of this. So just to show you that the optimization with the life cycle analysis allows you to compare technologies and allows you also to decide which are the best technologies. The only remark here is that we have made the calculations with two different indicators. So in LCA, we can have different measures of the environmental impact, and with the different indicators, we would have the same order of the technologies, which is to some extent difficult then to handle because it means that we have to arbitrate between two different indicators in the LCA. Yeah, we have also done this analysis with a three objective optimization. On one hand, the environmental impact, the profitability of the biomass, and the capacity of the plant. Okay, so I'm going also to show you why it is important to do process system design and not just process unit optimization. And the example is here. So if you have, sorry, at the end of the process, you have to separate the synthetic natural gas from the carbon dioxide. And you can use a system like this one, which is a membrane system, which is a four-stage system. You can see that it's a real superstructure with a lot of flows that have to be optimized. Okay? And that are combined. Okay? There are two different ways of doing it. The first one is to say, okay, I would like to maximize the methane recovery in my system. So I would like to have most of my product available as a product. And the other one is to say, okay, I would like to have an integrated version, mainly because some of the depleted flows, which are here, can, and this one, can be used as a heat source for my process. And if I'm using this as a heat source, it means that I will have less to take from the syngas, which means that I will have bigger flow here. Okay? And what the optimization has shown is that this is the best solution with a three-stage countercurrent if I want to maximize the recovery. And this is the best solution if I want to maximize the efficiency of the process. And in fact, I'm doing only 84% of recovery instead of 93. I'm not using the same technology in this system compared to this one. So the red one are still here. This is the other technology, but you can see that we are doing it in a very different way, which finally shows that with optimizing the recovery, we would have obtained this efficiency with a bigger area in the membranes, a bigger investment cost, of course, and a lower efficiency. So it means that in this case, it would have been a very bad idea to optimize the process unit because it was not the best conditions for the system integration. Okay? And this is important. The last remark is that there was no, I don't know. This was too much. Okay. Process design versus process integration. This is also something which is important. It's important to look at the whole system. And I give you just one example. This is the typical way we produce fuel from wood today. It's an ethanol process that is doing a hydrolysis, a fermentation, and distillation. This is typically what is done in Brazil to produce liquid fuel. Okay? Efficiency, 32%. Okay? In reality, the rest is here. It is converted into biogas, and the lignin that is here is dried and then burned into a steam cycle that is satisfying, producing the heat that is needed, and sometimes exporting, when optimized, a certain amount of mechanical power. But there are other ways of doing the same thing. Okay? Instead of doing of burning, I could gasify the lignin. And this will increase, in fact, the electricity production, still having 32% of efficiency in the ethanol production. But I can do even better because I can also gasify the lignin and produce synthetic natural gas. And now what you can see is that from the same amount of wood, I have the double production of fuel. Okay? So instead of having 32% of production, I have 70%. Okay? And I can even optimize the system by integrating the steam. But look at what did happen here is that if I'm producing steam to export electricity, so I'm producing more electricity here, what is happening is that I'm producing less synthetic natural gas. Okay? And the reason for this is that the heat from the synthetic natural gas here is used by the ethanol production. But the two heat loads have to match one with the other. Now, if I want to export electricity out of the system, I'm taking some heat, some energy out of the system. It means that I have less heat available. Okay? Which means that I will have less possibility to produce synthetic natural gas. And at the end, what we have found is that it was making sense to not only add steam cycle, but add also a heat pump, which is quite interesting because we are adding a heat pump, so it means that we are consuming electricity in order to be able to export electricity. Okay, so we are taking the heat which is below the pinch sending it above the pinch because we need heat for the ethanol production here. And by doing this, then we reach an efficiency of this one in which we have improved the overall production and we have exported electricity. Okay, so this is the proof that by doing integration we are quite we can be quite efficient with the system design. Now, what is interesting also is that the value that we obtain here with a mix of ethanol and synthetic natural gas is, from the lower heating value point of view, equivalent to the efficiency if we would have converted the wood into synthetic natural gas integrally. Which means also that then we have the possibility of having a mix of liquid and gas fuels produced from the biomass. Now I would like to answer your question. How do I select out of my list the best one? So what I'm going to do is that I'm going to say, okay, let us consider that I have a collection of processes, and let us consider that I know that my economical conditions are uncertain. So it means that I will have distribution functions. In fact, for my the cost of electricity, the cost of wood, the cost of gas, the cost of my equipment as well. Okay. Now I'm going to consider this, which means also that if I'm taking these points and then I'm recalculating it, the place where the optimum with the economical conditions will be different. Okay. So what we are going to do is the following. We're going to consider the distribution here and make a Monte Carlo simulation on the economic conditions. I'm choosing one objective function, which is total profit. Okay? Then by using a Monte Carlo, you know what is Monte Carlo approach? So Monte Carlo, you have distributions of the different parameters, and you draw one value according to its probability of appearance, and you create a collection of values randomly. And what we do here, it's 3,000 evaluations. So we take 3,000 sets of those economical parameters taken by randomly in considering the distribution which is there. Okay, so we obtain 3,000 set of economical conditions. For each of these conditions, we calculate the values of all the Pareto of the elements of all the Pareto. For each set, now I'm going to look at the solution, and I'm going to look who is in the top 10. Okay, so I'm taking all my designs, and for one randomly selected conditions, I'm going to look at who is the best, and I'm taking who is in the top 10. And if one configuration is in the top 10, it receives 1 point. I do it 3,000 times, and I look who has received the more points. Okay? And this one is the one that has the highest probability of being the best in the uncertain world of in the uncertain economical world. Okay? Which allows me then to identify who are the best systems. Okay? In this case, it was total profit. Okay? So, and I just show you what we have done for. So it was the wood price, the carbon tax, the yearly operation. So it's the expected lifetime, the interest rates, and the investment cost. Okay? And some of the and there are different distributions that can be used. Okay, some have a formula like this. For example, for the CO2, we said that okay, there is a highest chance that it will be high and low. Yeah.
So some operation for this Monte Carlo simulation is all the Pareto points, right?
Yeah.
So then take the decisions made with the fixed economic parameters.
Yeah.
Then you vary.
Yeah. So don't forget that we have not, when we have taken the decisions, we have not considered the total cost, but the investment and the efficiency. So the efficiency is related to the flows, and the total cost is just investment, not the total cost of the system, including the efficiency. So it means that we to some extent have a good chance of having the optimum there. Okay. Another way would have been to use a stochastic programming approach, in which we would have made the optimization by sending randomly selected parameters during the evolutionary algorithm realization. This would be an alternative approach. But nevertheless, it would not help me in taking the decision. Here, what is interesting is that I have a collection of design, and I'm going to select among this collection which is the one that has the highest probability of being the best. Okay, and then what we have done is that we have taken the Pareto curves that I had before, which is even richer here. So you can see that we have a very big list of different designs. Okay, and we can identify who. So the size of so the original points are in colors, but then when the size of the parameter is the point is increasing, it is proportional to its probability. So the number of points that design has received. And so, for example, you can see that those are this one and this one are the ones that have the highest probability of being the best. Okay. The advantage is that now I have a limited number of design that I can really compare one to one to have the final, to take the final decision. Okay? Yeah, this is the same. So my conclusion there, I guess that you are with. So you have seen that applying the same kind of techniques. So again, I'm combining process modeling, process integration, optimization techniques, and assessment methods. We are able to make the design of systems. We are able to take decisions, to choose technologies, to size the technologies, to size the processes, to adapt the processes to the supply chain, to finally propose the best solutions in which we have the highest confidence. It doesn't mean that this will be the final, that the decision is already there, but at least we have a very good knowledge about what are the directions or where the technologies will go in the future. Okay? Importance is that you have to do system thinking, and the second element which is important is that you can use optimization in order to identify what are the best scenarios. So you do not have to rely on your intuition to design scenarios. You can ask a computer to help you to do it, and all these things is at the end implemented into the Osmo platform that we are developing in my group, and that is really a computer-aided framework. So doesn't mean that you have to stop to think. You just have to use this in order to help you making the design. And something which is perhaps very important is that the value that of what we are generating as solutions is highly dependent on the quality of the data that you are using, so the parameters that you use in models. Okay? And of course, it means that we have to work with specialists. And it's important that if you need to clean the gas, that you discuss with specialists in gas cleaning. If you want to do gasification, it's important to discuss with those that are developing gasification. If you do methanation, you have to discuss with the people that do methanation, so that you are sure that your models represents the reality of the technologies. And what is important is that the people that is discussing with you on the methanation does not have to be a specialist in gasification. You can just collect their information to then place it into the whole system. Okay? Right. Do you have questions?